So we've already spent a good amount of time talking about what exponents do. What we want to do in this section is kind of learn a new type of notation that's really useful in the scientific community. So we're going to go through how to put something in scientific notation, how to convert it from scientific back to normal form, and we're going to go through all the details of that. But before we do so, we're going to work with 10 raised to a power. So we're going to kind of see some rules that follow as a result, because we know that power, or the exponent, is telling us how many times we're multiplying 10. So when 10 is raised to a positive power, something nice happens. The exponent really tells us the number of zeros that follow the 1. So to give you some examples, if we do 10 to the first power, that means you take 10 and multiply it by itself once. So you really just have 10. 10 to the second power is 10 times 10, which is 100. So looking at both of these, you have a 1 in the exponent spot, you have a single 0 following the 1. 2 in the exponent, you have 2 zeros following the 1. Then if we move on to 10 to the third, that would be 10 times 10 times 10 times 10. So if you plug that into the calculator, it is 1,000. So again, third power, there are 3 zeros following that 1. And then last but not least, if you have 10 to the seventh, yes, you can plug this into your calculator, but in the same pattern, you write the 1, and then it's followed by 7 zeros. So 3, 4, 5, 6, 7. And then we can fill in our placeholders to see that this is 10 million, okay? The other thing that you can kind of think of is really what you're doing is you're writing the 1, and then that exponent is telling you how many spaces you move the decimal. So 10 to the first would be 10. For 10 squared, you write the 1, you move the decimal twice, it's 100. 10 to the third, you write the 1, you move the decimal 3 times, it's 1,000. So it follows the same process, okay? So we haven't done too much with negative exponents, because what does it mean to have a negative number of times you multiply things? So this is where we're going to take the next extension to these exponents. So when 10 is raised to a negative power, the exponent tells us the number of places to move the decimal to the left of 1. So here we're moving the decimal to the right of 1 each time. Now a negative exponent is going to have the opposite relationship, okay? So let's start with 10 to the first power. We write the 1, and typically our decimal would follow right after it. Now I'm going to move it to the left 1 space. So 10 to the negative 1 is the same thing as 0.1. 10 to the negative 2 would be, we write the 1, the decimal is normally sitting here, and we move it 2 spaces to the left. So it's 0.01. 10 to the negative 3, again, we write the 1, and then we move the decimal 1 to 3 spaces, and we fill zeros in, just like above, okay? So 10 to the negative third is 0.001. And then finally, 10 to the negative seventh, we've got to move the decimal 7 places to the left, so I'm going to need a lot of room out front. We move that decimal 1, 2, 3, 4, 5, 6, 7 spaces, and then we fill in all of these bumps with a 0, okay? The other thing that I'm going to connect this to, because we're going to go through our exponent properties here, is if you think of 0.1, it's like 10 cents. This is exactly the same as 1 divided by 10. 0.01 is a penny. So this is 1 over 100. Or really, 100 is 10 to the second. And same thing up here, 10 is the same thing as 10 to the first. So what actually ends up happening is when you have a negative exponent, it's telling you to move that thing into the denominator position instead, and you're going to end up with a small fraction. So in the same way over here, 0.001 is the same thing as 1 over 10 to the third if you plug that in your calculator. And 10 to the negative 7 is the same thing as 1 over 10 to the 7th. Okay? So the reason we're going to go through this notation is if you think of just kind of everyday situations, there's a lot of very large numbers. Speed of light, huge number. U.S. national debt, gigantic number. Distance to the moon, a very big number. But then we also have a lot of very small numbers too. So we have stuff like the size of a nanowave. There's a lot of very microscopic things, or the size of an atom, that you can't feasibly measure. So it's something that requires a lot of zeros when you have a large or small number. So the scientific notation is really going to help us because we can display it in a much more condensed form. And then we don't have to worry if we're dealing with operations with these. So we're going to be working with a lot of exponents. So we're going to actually go through a few of our exponent properties. So we're going to try to rewrite both of these using a single positive exponent. So this ties into two of our properties. But thinking of 2 to the third times 2 to the second, this first piece really means 2 times 2. And the second piece means 2 times 2 times 2. So if I write this out, that's 2 times 2. And then we're multiplying this by 3 2's. So really what you're doing is you're taking 2 and you're multiplying it 5 times. And we know how to condense that with an exponent. This is the same thing as 2 to the 5th. So what we've actually done with these two exponents is we've just added them. This was the second, this was the third. They add together to give us that 5th power. When we have division, you know division and subtraction go hand in hand, so this one's going to turn out to be subtraction. So multiplication will turn to addition, and then division will turn into subtraction. But just to show you, 4 to the 5th means multiply 4 5 times. 4 to the third means multiply 4 3 times. And then just shrinking stuff down, 4 divided by 4 is 1, so these two cancel. Same thing, these 4's cancel because 4 over 4 is 1, and these 4's cancel. So 3 4's in the top cancel with 3 4's in the bottom. And what you're left with then is just 4 times 4, or 4 squared. So what we're actually doing here is we're taking the top exponent and subtracting the bottom. Okay? So these are going to be our two rules. When we multiply something with the same base, we're going to add the exponents. And if we're dividing something with the same base, we do the top exponent minus the bottom. Okay. So these are our two exponent properties. We're going to add exponents when multiplying. So to give you a quick example, if you do 3 to the 2nd times 3 to the 7th, the base stays the same. We add the two exponents together. So this condenses to 3 to the 9th. And to show you just another example off to the side, even if you have a negative exponent, same thing. So 2 to the 10th times 2 to the negative 5th would be 2 to the 10 plus negative 5. So it leaves us with 2 to the 5th. Okay. When we're dividing, we're going to subtract exponents. So here, 5 to the 9th over 5 to the 3rd would be this top exponent minus the bottom, leaving us with 5 to the 6th. Okay. I'll do another example in a second, but it relates to this one. If you have a negative exponent, you're going to switch the position in the fraction to change the sign of the exponent. So here, 3 to the negative 1 is sitting, you can think of it as the top of a fraction, because you can always divide by 1. So what ends up happening is you flip it into the bottom. So you get 1 over 3 to the first. Here, if you have 4 to the negative 2, it's in the bottom. So to make it positive, you flip it to the top. Okay, but you don't need to write the divided by 1 because dividing by 1 does nothing. So this just becomes 4 squared. Okay, so going back up here to another example, if I switch the order of these and I have 5 to the third over 5 to the ninth, you have more 5s in the bottom, so that's going to be where this thing ends up staying. So following our rules, we would do the top exponent minus the bottom, and that gives us 5 to the negative 6. So really what happens is it becomes 1 over 5 to the 6. Okay. So again, I had more in the bottom. That's where that exponent piece ends up staying. Okay. So now that we've got all of our exponent rules out, we're going to talk about scientific notation. The thing you have to be careful about is it's very precise how you write it. So we say a number is in scientific notation when a number between 1 and 10 is multiplied by a power of 10. So I've got 3 examples right here that have a form that's very similar to each other. You have some numbers times 10 to powers, but really only one of these is actually in appropriate scientific notation, and that's going to be this first one. Okay, so this one is in true scientific notation. Although these other two look very similar, the problem is this leading piece. You want a nice solid digit followed by the decimal. So it has to be 1 point something, 2 point something, 3 point something, up to 9. So here you have 0, that's a problem. And then for C, you have 10, that's a problem. So even though it has 10 to a power, these are not quite scientific notation. So what you need is 1 point something, 2 point something, 3 point something. And then I'm not going to write every single digit. The last number you can have is 9 point something times 10 to a power. Okay. So just be conscientious. You have to have a solid digit 1 through 9 immediately followed by the decimal, and then the trail end happens, and then times 10 to a power. So we're going to work on just converting back and forth between these. The number one thing you have to remember really actually goes back up to this first example. When we had positive exponents, we have very big numbers. So 10, 100, 1,000, 10 million. When you have negative exponents, you end up with small decimals. So the same idea is going to hold here, because also this told you how many times to move the decimal. That's all you're going to be doing with this. 10 to a power tells you the number of times you're moving the decimal. So you can remember your left and rights if you'd like to, but I personally am not a big fan of that because it gets confusing going back and forth between these. Really just remember that if you have a positive exponent, it should represent a big number. Negative exponent, gonna be a small number. So we're gonna start by, if I have a normal number, how do I put it in scientific notation? So the very first step you make is you're going to write a decimal point after the first non-zero number. Then you're going to count the number of spaces that you're moving the decimal from its original position. If the decimal had to move to the left, this means you're going to have a positive exponent. If the decimal moves right, you're going to have a negative exponent. Okay. And the exponent is exactly the number of spaces that you moved. That's going to be what your power of 10 is. So to just kind of give you an example here, if you had 8 million, your decimal sitting right here, this should be a big number. You would have to move it after the first non-zero number, which is the 8. Okay, so you have a big number, it's going to have a positive exponent. And then in this case, because you're moving the decimal 6 spots, it would be 10 to the 6. In the case that you have a very, very, very small decimal, you do the same thing. You're going to move the decimal after the first non-zero number, which in this case would be a 2. And your exponent is going to be negative because you have this small decimal. And the actual exponent in this case would be 1, 2, 3, 4, 5, because we moved it 5 spaces. So it would be times 10 to the negative 5th. Okay. So let's try some examples. We're going to write each of these numbers in scientific notation. So for this first one, first thing I need to do is I need to write the decimal after my first non-zero number. 3 is that first non-zero number. So what I do is I write the decimal after it, and then I keep copying down all of the important digits that I see until I hit this trail of zeros. I don't have to worry about zeros because remember, those are just the placeholders that we fill in the place. Okay. So in this case, originally in this number, my decimal was sitting here. So it's moved 1, 2, 3, 4, 5, 6, 7, 8 times. Okay. So what that means is I'm going to times this by 10 to a power, and that exponent is going to be exactly 8. So it's a big number. That means it's a positive exponent. Okay. So same thing in B, it's a big number, immediately tells me it's a positive exponent. Currently, the decimal sits here, it's 10,375. And I want to move it after my first non-zero number, which is this 1. So in this case, it's moving 4 places. So in scientific notation, I would put the decimal after this first non-zero number, and I copy everything down until I hit a trail of zeros or the end. So in this case now, we times this by 10, and my exponent is going to be positive 4 because it's a big number. In these next two examples, you see we have small decimals for both of these. So both of these are going to have negative exponents. So same idea, I search my number until I hit my first non-zero, which in this case is 5. So my decimal is going to move to immediately after the 5. And then I copy everything down until I hit the end. So you see we're also copying the 0 that's sandwiched in between each of these because it's significant within those two. And then this is going to be times 10 to a power. In this case, our decimal moved 1, 2, 3, 4, 5 places. So it gets negative 5 as the exponent. So if you have a decimal or a small number, that means you're going to have a negative exponent. Okay. So same idea here. I search my number until I hit the first important one, which is the 1. So I put the decimal immediately after the 1 and copy down all the significant digits. And then I count the number of spaces I move, which is 3. And so that tells me since this is a small decimal, it's 3, and the exponent is negative. Okay. So I like thinking of this approach a little bit better because it makes life a little easier when you're doing the opposite. Because now if I give you a number in scientific notation and want you to convert it, you really have to do the opposite direction, which is why I don't like remembering left and right. So here, if the power of 10 is positive, so positive on the 10 indicates this should be a big number, which means like here, in this case, you have 10 to the 8th, it should be big. I'm going to move the decimal this direction to get a large number. So we're going to move the decimal right that many places and add zeros as we need to. In the case you have a negative exponent, like in this second example, that's going to have to give us a very small decimal number. So I'm going to move my decimal in the left in this direction. Okay. And so that's all we have to do to convert back and forth between these. So for these, I like to give myself a little bit more room. I'm going to be making a big number here because it is a positive exponent. And I'm going to start by just copying all of the digits that I see, 50142. The decimal is currently sitting right here, and I need to move it 8 places and make a big number. So it's 4, 5, 6, 7, 8. So I'm moving my decimal in this direction and then filling in zeros as needed. So it's now a little bit hard to add in our placeholders that we're used to. So I'm just going to recopy the number and then add those in. Okay. For B, because we have this negative exponent, it tells me I should be making a small decimal. So in this case, I'm going to need more room out front to make that small amount. Currently, my decimal is sitting right here after the 8, and because my exponent is a -4, it tells me move 4 spaces. And I'm going to make that small decimal, so that told me the direction to move it. Okay? And then you can put a 0 out front if that's what you're used to. But in standard form, this would be this decimal.